Have you ever played tug of war? Imagine two people pulling on a rope, one stronger than the other. Now imagine two atoms pulling on shared electrons. That's exactly what happens during chemical bonding. Welcome back, young chemists. Today, we dive into the electrifying concept of electronegativity, the ability of an atom to attract the bonding electron pair when combined in a compound. Let's break that down with an example. In hydrogen chloride, that's HCl, hydrogen has an electronegativity of 2.1, while chlorine has 3.0. So chlorine pulls the bonding electrons more strongly, the electron cloud shifts towards chlorine. We represent this shift using a delta minus on chlorine and delta plus on hydrogen, indicating a polar covalent bond. Now, if two atoms have very different electronegativities, say like sodium and chlorine, the electron is completely transferred, forming an ionic bond. On the other hand, when two atoms have nearly equal electronegativities, like carbon and hydrogen, they form a nonpolar covalent bond. The electrons are shared equally. As you can see in the visual, we compare the electronegativity of sodium and chlorine in various bonding scenarios. This explains why salt, sodium chloride, forms an ionic compound. Electrons move entirely to chlorine. Now let's uncover what influences an atom's electronegativity. First, atomic size. As the size of an atom increases, the nucleus finds it harder to attract the bonding pair of electrons. So, electronegativity decreases with larger atomic radii. Second, nuclear charge. A higher positive charge in the nucleus exerts a stronger pull on the bonding electrons, leading to greater electronegativity. But here's the key, both these factors operate similarly to how they affect electron affinity, since in both cases, the atom's ability to attract electrons is being measured. Let's take fluorine as an example. It's tiny in size and has a high nuclear charge relative to its size. So, it's no surprise that fluorine is the most electronegative element in the periodic table. Compare that to cesium, a large atom with lower nuclear pull, its electronegativity is very low. Think of it like magnets. Small, tightly packed magnets attract metal better than large, scattered ones. Now, what happens to electronegativity as we move from left to right across a period? First, the atomic size decreases. The outer electrons are pulled in closer due to increased nuclear charge. Second, the nuclear charge increases. More protons mean a stronger attraction for bonding electrons. Together, these changes cause electronegativity to increase across a period. Let's take period 3 as an example. Sodium with an electronegativity of 0.9, magnesium 1.2, aluminium 1.5, silicon 1.8, phosphorus 2.1, sulfur 2.5, and chlorine, the highest, 3.0. This tells us that metals on the left tend to lose electrons and are electropositive, while nonmetals on the right have higher electronegativity and tend to gain electrons. In short, electronegativity increases across a period from left to right. So, the rightmost nonmetals are the true electron lovers of the periodic table. Alright, let's now go down a group. As we descend the group, something important happens. The atomic radius increases. This means the bonding pair of electrons is farther from the nucleus and less tightly held. Even though the nuclear charge increases, it is shielded by more inner shells. This is known as the shielding effect. So overall, the electronegativity decreases down the group. Let's look at group 17, the halogens. Fluorine, at the top, has the highest electronegativity, 4.0. Then comes chlorine, 3.0, bromine, 2.8, and iodine, 2.5. Why is this important? Because fluorine's high electronegativity makes it one of the most powerful oxidizing agents. And as we go down the group, The atoms get larger, the nucleus gets more shielded, and the attraction weakens. Electronegativity is not just a fancy term, it's a game changer in chemical reactions and compound formation. Let's see how. First, it helps us predict bond type. A large difference in electronegativity, say between sodium and fluorine, means an ionic bond. A small difference, like in oxygen and hydrogen, means a polar covalent bond. Second, electronegativity influences chemical reactivity. Highly electronegative elements like fluorine and oxygen are strong oxidizing agents. They pull electrons away in redox reactions. Third, it affects acid base strength. In oxyacids, the more electronegative the central atom, the more it pulls electrons away from the oxygen hydrogen bond, making it easier to donate the H plus ion, increasing acidity. Fourth, in biological systems, oxygen's high electronegativity plays a critical role in cellular respiration. In the mitochondria, oxygen pulls electrons down the electron transport chain. Let's quickly revise what we've explored about electronegativity. Electronegativity is the measure of an atom's tendency to attract the bonding electron pair toward itself. As we move across a period, atomic size decreases and nuclear charge increases. So, electronegativity increases. As we go down a group, atomic size increases and shielding dominates. So, electronegativity decreases. Remember, elements with high electronegativity like fluorine and oxygen are key players in oxidation, acid strength, and biochemical electron transfer. So, to wrap up, electronegativity helps us understand why bonds are polar or ionic, why some elements grab electrons eagerly, and how molecular behavior changes based on atomic attraction. I hope this session helped you see how electronegativity is not just a trend. It's a chemical compass that guides bonding, polarity, and reactivity across the periodic table. See you in the next class with more chemical insights.